Not yet? Yeah. Can go. Okay. So first of all, I would like to thank the organizer for the invitation, and particularly for putting me into this session, into this canonic session, which brings me back to my initial interest about music and mathematics, starting from a very specific musical problem. And I would like to start with this problem, which tells you a little bit about the emergence of tiling rhythmic canons in music. It's a composition by Olivier Messiaen, Haravi, for piano and voices, in which you can find this, what he calls triple non-invertible rhythmic canons, not in the same sense. It's using non-invertible rhythms, which are kind of privileged materials, which are palindromic structure, basically. But let's listen first, and then I will comment a little bit. The soprano is finishing singing, and then starts this piano canon. As you can see from the quote, it's in French, but I think it's clear. I will translate it. The result is that all the different sonorities, they mix together, and they oppose to each other in a very different way, never at the same moment, neither at the same instant time. And that's what he calls organized chaos. Okay? It's very kind of metaphorically speaking, it's clear that what he's trying to do is to tile the space from a mathematical point of view. And there is a second volume of his treatise of rhythmic color and ornithology, which is entirely devoted to canons, to these canonic constructions that you can find also in other pieces, like, for example, Adieu for two pianos. So this is an example maybe of creativity, of transformational creativity, or kind of exploratory creativity, putting one structure into another context by producing a different piece. But the point here is that when you look carefully to the rhythmic structure, so forget about Messiaen limited transposition modes and all these wonderful sonorities, but just focus on the rhythmic part of the canon. So on the onsets, actually, you see, there are onsets coming together, and actually at the end there are a lot of onsets coming together. So it's not exactly what we can call a tiling canon. I can make you listen this brief passage here. So many superposition at the end, many holes, which is not exactly what we want if we want to tile the space, and this is basically because he was using tools which are not exactly the tools that can enable you to grasp the tiling process. So he was using palindromes, like patterns. So the canon is based on the translation in time of this pattern, which is a concatenation of palindromic structure. You see 3, 5, 8, 5, 3, juxtaposed or concatenated with 4, 3, 7, 3, 4, etc. And actually there is no relationship between palindromic structure and tiling process. Okay, so but the idea is I can say that there is something in Messiaen's which kind of links, make the link between composition and tiling process. So this, for me, is a prototypical example of mathematical problem. So what I call a mathematical activity, this is a schematic kind of vision you have a starting point, which is a musical problem. Then you try to formalize. You enter in the mathematical realm here for the mathematical statement. Then you generalize. You have eventually new theorem, a general theorem, also old theorems. You rediscover old results, but since you started with a musical problem, that's also an interesting achievement. Then you go back to music. And in this application, you can use kind of computer-aided softwares in order to really providing modeling for composers. And this is what we are doing with our open music visual programming language at IRCAM. So this is a general scheme that you can apply a lot of interesting mathematical problems. If you are interested to know a little bit more about the way in which musical problems touch some interesting mathematical constructions, here there is a small list, 7 problems that I was studying in my research, and you can find in my habilitation thesis, so a kind of detailed description of all of them. So tilings, homometric structures, which are related to what we call Z-relation in music. I will come back at the end because there is a deep connection between homometry in crystallography and tiling process in music. Then you have Neo-Riemannian analysis with Kempenhauer networks that you can formalize in categorical way by using category theory, formal concept analysis, so with the idea of lattices, partial order lattices, maximal even sets, with the idea of using Fourier transform in order to formalize scales, projective geometry, periodic sequences, and finite different calculus. So this is for the mathematicians who are interested, but also for the musicians, because all these are basically musical problems at the beginning, and then you can have nice, interesting mathematical results. And you see the place of computer science here kind of has been enlarged because you can also use modeling in the kind of formalization process. And typically, when you study, if you study Hamiltonian processes, Hamiltonian paths in the tonnets, it's very difficult to have a mathematical theory of that. It's better to implement and to see all the space of solutions. So there is a really kind of ubiquitous way of putting these models, these computational models. So let's now enter into really the subject of this presentation, which is the tiling process. Let me give you an example, musical example of what is a tiling canon. So forget about pitches and just focus on the rhythmic dimension. And the tiling canons is something like that. Okay, so you are tiling the line by translate of one tile and one pattern, which is just this one, that you translate in time 3 times in such a way that you have 3 voices, or 3 parts, rhythmic tiling canons. Actually, you are not tiling the line, you are tiling the circular representation, the cycle, because there is an old result by De Bruijn saying that if you are starting with a finite pattern, then you tile the line by translation, then your tiling is periodic. So you end up with tiling the cyclic group. There are many different ways to formalize this tiling process. One easy way is to look at this as a set theoretical operation. So you're taking your pattern, then you translate, you transpose, if you want, or translate in time, and then you make the union, and you have your tiling. There is another way, which is much more algebraic. You take the notion of factorization of a cyclic group into 2 subsets. What does it mean? It means that every element of the cyclic group, of the circular representation, is written in a unique way as a sum of an element of A. A is the voice of the canon, and B is the enters of the coming in of voices. So in this case, you have a voice which is down, 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 and the coming in is 048, which is the regular kind of coming in of voices in every 4 steps. There is actually another way to look at this is a kind of is using polynomials representation. It's is equivalent. Instead of writing the pattern as residual classes of cyclic group 0, 2, 5, 7, you just write as a polynomial, a 0, 1 polynomial, having exponent equal to the numbers here. So x to the power 0 is 1, x to the power 2, x to the power 5, and 7. And then you make the product of polynomial. Of course, you have to be careful that every time you have a x to the power 12, this is equal to 1. So you make the product modulus x12 minus 1. And a tiling is just the fact that you are tiling the polynomial 1 plus x plus etc. So basically the regular poles into a product of two polynomials. This is very useful when you are using, for example, theory of cyclotomic polynomials. They are playing the cyclotomic polynomials are playing the role of prime numbers in the decomposition of numbers. So they are playing the same role in the decomposition of general polynomials. And so you have a already made theory that enables you to grasp this tiling process. So I was interested in kind of classifying a little bit the cases. Which kind of tilings can you have? The easiest tiling you can have actually is when the pattern and both the pattern, so the basic voice of the canon and the coming of voices are regular. They are, mathematically speaking, they are subsets, subgroups of the cyclic group. And here you also have a nice commutative relation, which is kind of a duality principle in music. If you have a canon, for example, the first case, you have a canon with 3 voices. Every voice has 4 onsets. Then you can just rotate, and you have a canon in 4 voices. Every voice has 3 onsets. So this is just because the direct sum is commutative. But musically speaking, makes a big difference. So this is the first case, easiest case, that you can just, from a mathematical point of view, you use Silov decomposition theorem, and then you are everything what you want. There is another case which is interesting. One of the subset is not a subgroup; it's just a subset. For example, here you see this pattern is not regular, a regular polygon on the circle representation. So this is a little bit more complicated. But the coming in of voices are regular. So I will show you an easy algorithm to obtain all these canons in this second group, in the second possibility. Then the third possibility is to have both the voices and the coming in of voices which are not subgroups, which are not regular. And as you see here, for example, you have this pattern and the coming in of voices, which is not a regular polygon, which is not so a subgroup, but it has something which remembers Hugh Messiaen. Messiaen was working on transposition limited modes which are invariant up to transposition, up to rotation, if you want. And rhythmically speaking, this is an example. This is an example of Messiaen mode in the rhythmic domain. So the question is really Messiaen property mandatory of the tiling rhythmic canon? Can you construct canons which have not this property? Because, as you see, in the three cases, in the subgroup case, in the subgroup here, I mean, one of the factors is periodic. It has this Messiaen property. So before giving the answer, let me just explore with you a little bit more into detail. Noam mentioned the Pygmy music and this canonic process. Actually, this is really linked to what I want to tell you. There are studies by ethnomusicologists such as Sima Rom and Marc Chemillier who show actually that Pygmy used canons, a rhythmic pattern which have kind of auditive properties. What does it mean? There are patterns like this. You see, there is a kind of permanent syncopation, so it's very difficult to grasp for us. Why? Because every time you trace a diameter into this pattern, at the end of the opposite side of the diameter, you have no onset. You cannot split the pattern into two parts. Okay? So this gives you this idea of shifting, permanent shifting. And so colleagues from the States, they generalized this approach with the kind of notion of K asymmetrical rhythmic pattern, in which instead of looking at diameter, you're looking for equilateral triangle. So you're doing the same, starting from every onset here. Okay, you're doing, and you see. And if you add the condition that at the end you really want to fill entirely the space, you end up with a tiling, the tiling of the circular representation. Okay, and you see, you can build a catalog. So these are tiling canons in which voices are entering in a regular way. See, and just give you an example. That was at the end, so let's listen again. Okay, well, of course it's boring because the dimension is very low, the period is short, so you are obliged to repeat things, and the voices are entering in a regular way. So, by the way, the point I wanted to make is that there are easy ways to construct all these canons by regular entries. And the easiest way I found actually is using a kind of permutational construction, permutational algorithm. So imagine you have 6 numbers from 0 to 6, so 0 to 5, 6 equivalent to 0, mod 6. And you want to tile the space. So the easiest way to do is just to take the cluster, the chromatic scale if you want. So repeat it again. So this corresponds to the permutation 0, 1, 2, 3, 4, 5. Okay? But then you can have another permutation, for example, say 0, 5, 1, 3, 4, 2. And what you do is just to put these numbers into a space, is a regular into a cyclic representation, which was period is a multiple of 6. For example, 18, but you can choose 12, you can choose 24. And if you do that, so 0 is here, 5 is here, 7 is here, okay? 0 is here, 5 is here, then you have 1, but 1 is already in the back, so you have to think mod 6, okay? So 1 is 7, is here. Then you have 3, 3 becomes 9, 10, then 14, and at the end you have again a 3 asymmetric rhythm, so a tiling canon by regular coming in of voices. The interesting point is that's very easy for all composers. They can really just permutate numbers, and you have a 3-voice canon here, but you can also, with the same pattern, have 4-voice canons, just by using, instead of 18 as a period, 24, and so on. Okay, so just now we have something which is much more interesting, musically speaking. Okay, but we are not answering the question I was telling you, I was asking, is Messiaen property, is this transposition limited property mandatory for tiling process? Actually not. Not because there are canons, special canons, which we can call aperiodic rhythmic tiling canons, or VUSA canons. They come from the work of mathematician Dan Tudor-Vusa, who formalized the model theory by composer Anatol Vieru. And as you see here, you have this big cycle of 72, which is factorized into 2 subsets, so the rhythmic pattern and the coming in of voices. In both cases, you have no symmetry, rotational symmetry, no Messiaen property. So let's listen what does it mean musically. Okay, so every part is just 1 note, for the pedagogical example, and then I just project in 1 line, so you build a melody. And what's the property of this melody? This is the most complex melody you can build in the space of 72. You cannot split this melody into smallest part, smallest component, because it corresponds to a word which has maximal length. In word theory, for example, if every voice is say a letter, A, B, C, D, so at the end you have a melody or a pattern or a word which is which is a Linden word in word theory, which is kind of maximal. Okay, so this is a really interesting object, both from musical point of view and mathematical point of view. And actually, from a mathematical point of view, this goes back to an old conjecture by Minkowski, a very easy conjecture to explain. Minkowski was conjecturing that in any simple lattice tiling of the n-dimensional Euclidean space by unit cubes, some of the cubes, so at least two of the cubes, must share a complete n-1 dimensional phase. So if you are in the plane, this means that if you are tiling the plane, the two-dimensional space with just squares, at least two of the squares, they have one side in common. Okay? You can prove that there is a kind of infinite number of squares having these twin properties, an infinite number of twins. Okay, so easy to show in dimension 2 and dimension 3, and Minkowski said, okay, no problem, I will prove in any dimension. No? And actually, he just gave up. He couldn't prove. And 40 years later, mathematician Hijos, he put this problem, this geometric problem, into a factorization problem, and he solved the conjecture. So he showed that this is true for any dimension. There is a wonderful book by Stein and Szabo, Algebra and Tiling for the Chaos Mathematical Monographs, for those who are interested in the history of this conjecture. And the point is that Wusa canons are exactly special cases of factorizations of what we call nowadays in algebra non-Ayush groups, groups not having the Ayush properties. So this was my personal contribution in the years of math studies in Italy. I put together these two domains, so the conjecture by Minkowski and the Ayush solution, with the new constructions proposed by Jan Tudor Wusa, showing that actually these canons that you can build, these non-periodic canons, they only exist in periods such as 72, 108, 120, so in periods which are not a power of a prime number, not a power of prime number multiplied by a second prime number, etc. So there are constraints. If you are kind of selecting, putting away all these conditions, you end up with 72, which is 2 times 3 times 2 times 3 times 2, so 2 to the power 3 times 3 to the power 2, which is not in this case, you see. So you are sure you can build non-periodic canons. This corresponds also to a well-known sequence by Sloan sequence. And then, interestingly, there is a connection with the open. There is a connection with the open conjecture in mathematics, which is Fuglede conjecture. It's a conjecture in spectral theory. And if you are interested, we devoted a special issue of our Journal of Mathematics and Music on this mathematical problems, contribution by mathematicians exploring really the Fuglede conjecture and showing how music can really can grasp this conjecture. I won't enter into detail, but just for the mathematicians who are here, I would like just to give the idea. What is the Fuglede conjecture about? Is an equivalence between tiling and spectrality of a set. So a subset of the Euclidean space is spectral if basically it has a decomposition of Fourier, Fourier decomposition. So in dimension 1, it corresponds to so you can put in, so you can kind of reduce this conjecture in dimension 1 and becomes a conjecture of the integers. And so it becomes really our tiling problem. And interestingly, this conjecture is false in dimension greater or equal to 3. It has been shown by mathematicians such as Terence Tao, Konontzakis, etc. And still open in dimension 1 and 2. In dimension 1 is really our case, our musical case. And so here is an example, a spectral set which tiles, it has a spectrum, it tiles the line. So the problem is, can you find tilings? Can you find kind of rhythmic patterns which tile the space by translation, but they are not spectral? This would be the counterexample of the Fuglede conjecture. And our colleague Emmanuel Agnew showed that actually all the types of canons which are aperiodic, so which are not VUSA, they are spectral. Okay, so if you want to disprove Fugate conjecture, just throw away all these trivial solutions and just focus on the VUSA canons, because this conjecture is true or false, if and only if it is true or false in VUSA canons. Okay, so this gives you an idea of the interest of these objects. So if you want to explore a bit the computational aspects, we implemented algorithms in open music. And we detailed, actually, there is a special issue which has been published in Perspective of New Music recently about canons and tinings. So you will find a detailed description of the algorithms which have been integrated into the math tools environment in open music, which enables you to obtain a large family of VUSA canons, but not all. Unfortunately, we have discovered that the algorithm is not exhaustive. So we still need an exhaustive algorithm in order to factorize a cyclic group into two non-periodic subsets. I mean, it's easy to say, but not easy to obtain. So when we started this implementation, then composers became interested in exploring compositional process. So we had several collaborations at IRCAM with young composers writing pieces starting with this model. So they didn't want to enter into the mathematical, of course, notions, but having a model in open music, having algorithms, they could produce a lot of varieties of different stylistic canons having this tining property. So let me show you some examples. For example, the first one was Fabien Lévy, a piece by orchestra, for orchestra, coincidences for 33 musicians. The idea here is using tiling process not in a kind of punctual way, in a kind of onset way, but really build morphological structures, big kind of objects, like, for example, here, ascending glissando, followed by, so repeated 6 times. So we are in a 6-part VUSA canon. And with the idea that when you just listen, and then maybe I can tell you a little bit more about the compositional idea, but we can maybe listen to this very first example of VUSA canons for composition. I think this interesting point here is that you don't hear the canon anymore. Huh? You hear melodies in between voices, and these melodies emerge as a kind of in a complex system. You have emergence of local properties, and because the ear tries to put kind of logic between the different voices, and so this was a kind of use of Vusa canon in a not canonic way, if you want. And then several other composers, such as Georges Bloch, for example, explore what Noam called the compound canons. If you have a 6-voice canon, for example, and you put the 3 first voices together, this makes 1 voice, and then the second 3 voices, it makes another voice. So you end up with a 2-voice canon, every voice being a 3-voice canon, you see? And that's the typical things you have to do in such a huge structures, because 6 is the minimum number of voices in order to produce these canons. You cannot have Vusa canons for 4 voices or 4 parts or 3 parts. This is the constraints, the mathematical constraints. But still, I mean, composers were able to use such a constrained kind of form in a very free way, by also applying, for example, standards, jazz standards, and kind of pushing a standard into the grid of a canon. So if you're interested, maybe we can discuss later, and I can show you many more examples. And there is also a book, the OM Composers book, that Gerard Assayag mentioned in his lecture, where you can find the detailed description of this compositional process. So let's just briefly go through other compositional uses. So Mauro Lanza, this description of the diluvio, la descrizione del diluvio, makes use of a huge canon of 6 + 8 voices, which means 14 voices canon in the period 392, and he was interested in a kind of quasi, almost periodicity that you can find in Vusa canons. As I said, Vusa canons, you don't have inner periodicity, because this is the constraint, but if you take one solution, for example, this one, this is the rhythmic pattern of one voice, then you are looking to the kind of regularities that you can find, and you see there are kind of periodicity, a small periodicity, you know, small patterns which are repeating. Not exactly, there cannot be just one pattern repeating itself and kind of structuring all the rhythmic part, but you can have this local periodicity which can help composers to grasp a little bit the kind of the listener process, because otherwise in such a big space you are very quickly lost. Okay, so pieces like this one for electronics and orchestra, maybe just a short except of this one. 3, just, and then I go to my conclusions. Okay, here's the canon coming in. Okay, so you have an idea. Daniele Ghisi, young composer, you will listen to him in a concert on Sunday, also exploring canonic processes. Then quickly, you can use polynomials, as I said, and you end up with what we call the cyclotomic timing canons, using cyclotomic polynomials. We have a couple of papers explaining the process, and again, in math tools, you can. This makes use of sophisticated conditions that we find in a paper by Koven-Meyerovich, the two mathematicians, published in the Journal of Algebra. And these two conditions actually are a sufficient condition in order to tile the space. It's still open the question of whether there are also necessary conditions for every tiling every pattern to tile the space. Then, of course, it's nice to have tiling by translations. But it would be also nice to have tilings by augmentations, like Bach did in the Goldberg variations, where he kind of, or the musical offering, where he's stretching the patterns. And so that this is a new also process that you can study. You have patterns tiling just by simple translation, like this one, for example, and also by augmentation. So if you augment, if you stretch the pattern. So that just give you an example of this. This is a Steve Reich-like pattern of the clapping music. It's not exactly the same. It's just a ta-ta-ta-ta-ta. Okay, this is the first kind of the beginning of the pattern used by Steve Reich. But as you see here, this pattern only tiles by augmentation of 5. So which means you have to stretch all the onsets by multiply the distance by 5. And so you end up with canons like this. Which are still open to compositions if you are interested. Composer Tom Johnson made use a lot of these augmentation processes in what he calls perfect tilings. You have a perfect tiling when you have a rhythmic pattern which is stretched every time of a different factor. Okay, so you have here five parts canon. Every part is stretched by identity, by 2, by other factors. Okay. So there is an entire cycle, tile work, which is exploring this process. So, by ending my presentation, I would like to come back to a question that was raised by Jean-Pierre Bourguignon yesterday. Can you hear the shape of a drum? You remember? Can you hear the shape of a canon? Actually, this actually is really an interesting question, because this brings you in another realm, which is a crystallography theory. In crystallography, you have crystals which are equivalent. They have the same diffraction, but they are not kind of superposed. It's not possible to superpose, to find the isometry, transforming one crystal into another one. And this is something that we know very well in music. If you sit on the piano and you play just 6 notes in the octave, this is an hexachord. Then you play all the notes you haven't played. This is the complementary. So between an hexachord and its complementary, there is always the homometry relation. What does it mean? Homometry means that these chords have the same interval content. They have, mathematically speaking, they correspond to polygons. They having the same distances, you see. So the distance 1 is twice here. The distance 2 is twice in both cases. The distance 3 is twice, and so on. So this is what music is called interval vector, and what is in homometry theory is just the distances of points. So can you hear the shape of a canon? No, you cannot hear. You cannot hear. Why? Because you have patterns like this one, for example, which ties the space by translation of a regular polygon. Then you have a second pattern. So again, this is an example of 3 asymmetric rhythmic pattern. Then you have a second pattern, which is homometric to the first one. Okay, as we've seen, they have the same intervals. does it tiles the space or not? Yes, it ties with the same subset coming in of voices. So you have homometric kind of tiling canons, so homometric structures, which means that you cannot hear the shape. The spectrum is not enough. The spectrum is basically the interval vector. If you make the interval vector, it's a convolution function of characteristic convolution of characteristic function. Then you introduce Fourier transform. Then you have sophisticated tools. This is really another topic which is not possible to sketch in this presentation. So I thank you very much for your attention.